This topic is about using prior knowledge of surface area and volume of 3D shapes to form equations and then using calculus and the theory about stationary points to find maximum and minimum in a real-life problem. So we'll go through various examples. The first example says the sum of two numbers is 92. So we'll let S represent the sum. Find the maximum value of the product, which we'll represent using P. So what we do know is the sum is equal to 92. The sum of two products, what we need to do is let X and Y be the two numbers. So let X and Y be the two numbers. Then the sum is also equal to X plus Y. So you've got equation 1 and equation 2. Both of them represent S, which implies that X plus Y must be equal to 92. Which implies if you want to make Y the subject of the formula, Y is equal to 92 minus X. Okay, find the maximum product of the maximum value of the product. Now the product is X times Y. But since obviously Y is 92 times X, 92 minus X, then product could also be equal to X times 92 minus X using 3. Okay, now because we can expand it, so that means P is equal to 92X minus X squared. So we've got P is the subject of the formula and we have everything in terms of X. Then we can differentiate P in terms of X with respect to X. Then we get 92 minus 2X. Now at the maximum value, we know dP over dx, so derivative of P with respect to X will be equal to 0, which implies 92 minus 2X is equal to 0, which means 92 is equal to 2X, which means X is equal to 92 divided by 2, which is equal to 46. If X is equal to 46, since X equals 46, Y is equal to 92 minus X, which is 92 minus 46, which is equal to 46. So the maximum value of the product is remember X times Y, which is equal to 46 times 46. If I put that into my calculator, I get 2116. Now, if I want to check whether this is a really a maximum product, then what I need to do is find the second derivative, which is d squared P over dx squared, which is if I differentiate this, then I get minus 2. Now, minus 2 is less than 0. Therefore, X is equal to 46 is when maximum P occurs. So that is true. Okay, so the maximum value of the product, so maximum P is equal to 2116. Okay, let's do another example. It's a very similar example, but it's a worded problem in this one. So let's see how we set this one up. A corner of a garden is bordered by two walls at right angles. So garden, we're assuming it's a rectangular. Okay, bordered by two walls at right angles. So that means it's bordered probably at two, only this part is bordered. So two walls, not all four. Okay, a garden has 30 meters of rabbit fencing. What is the largest rectangular area he can fence off? Okay, so we've got obviously two lengths involved. So let's call this X and y, then we know because he's fencing only these two lengths, then we have x plus y is equal to the 30 meters, which implies y is equal to 30 minus x, if you want to make y the subject of the formula. Now the rectangular area is equal to x times y, which means area is equal to x times 30 minus x, if we call this 1, using 1, which implies a is equal to 30x minus x squared. Okay, if I want to find the largest rectangle, so I'm looking for a maximum, then I need to work out the derivative of a with respect to x, which is equal to 30 minus 2x. At maximum, dA over dx is equal to 0, which implies 30 minus 2x is equal to 0, which implies 30 is equal to 2x, which implies x is equal to 15. When x equals 15, y is equal to 30 minus x, which is 30 minus 15, which is equal to 15. So maximum area is equal to 15 times 15, which is equal to 225 meters squared, because the unit was in meters. Now, if I want to check that this is when the maximum occurs, then I need to work out the second derivative. The second derivative comes from differentiating this one. So I get, again, when I differentiate this, I get minus 2, which is less than 0. Therefore, this is the maximum. Maximum occurs at x equal to 15 meters. Okay, next example. A closed plastic cylinder used for making compost has a base radius r. So a cylinder. I draw my cylinder out like this, is closed. So we have the top and the bottom. The surface area of the cylinder is 30,000 centimeters squared. So A, first thing I know is surface area is 30,000. Okay, and also we do know, and then so part A says show that the volume of the cylinder is given by this formula. So I'm trying to get to that. We also know the surface area is equal to, in a cylinder, is going to be the two circular parts. So the top and the bottom, remember there's a bottom here, is equal to, so each circular part is pi r squared, so it's going to be 2 pi r squared plus this part, which is this part, which is equal to, the curved part is equal to plus 2 pi r h. Let's write that again. So the two circular part are 2 pi r squared and the curved part is 2 pi r h. Okay, now if we combine these two, because they're both representing surface area, we get 2 pi r squared plus 2 pi r h is equal to 30,000. If we divide by 2, I get pi r squared plus pi r h is equal to 15,000. Okay, because I want to, if I look at this, what I'm aiming for, there's no h there, so that means I need to make h the subject of the formula. So which means pi r h is equal to 15,000 take away pi r squared. H must be equal to 15,000 take away pi r squared over pi r, which means if I separate the two terms out, I get 15,000 over pi r take away r. Now try to find the volume. The volume of a cylinder is given by the formula pi r squared h, which I know, so if I call this 3, then the volume is equal to pi r squared times 15,000 over pi r take away r using 3. If I multiply it out, I end up getting V is equal to pi r and pi r cancel out. So I get 15,000 r, which is what I wanted for the first term, and then I get pi r cubed. So I've just shown that that is true. Find the maximum value of the cylinder and using calculus show that this value is a maximum. Okay, so let's do the next part. So B, I've got V is equal to 15,000 r minus pi r cubed. So I need to first work out dV dr, because we got V in terms of r, so differentiate V with respect to r, which means I get 15,000 minus 3 pi r squared. Now we know at maximum dV dr is equal to 0, which implies 15,000 minus 3 pi r squared is equal to 0, which means 3 pi r squared is equal to 15,000. If I divide by 3, I get pi r squared is equal to 5,000. R squared is equal to 5,000 over pi. R is equal to square root of 5,000 over pi. Now we only take the positive square root because radius is a positive value, which is equal to R is equal to 39.8942 blah blah blah. If R is equal to that, then in order to find the maximum volume, I need to substitute into the V formula. So if I call this 4, so substitute R is equal to 39.8942 into 4, then I get V is equal to 15,000 times 39.8942 blah blah blah. Take away pi times 39.8942 blah 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 cubed, which gives me a value of 398,942.2804 blah blah blah. If I round it to 2 decimal place, that is equal to 398,942.28. It was measured using centimeters, so it will be centimeters cubed. Let's rewrite that again. Okay, if I want to check whether this is really a maximum, we need to differentiate it again. So if I do it here, so if I do d v squared over dr squared, so I differentiate this again, then I get minus 6 pi r. So what is this, the value of this when r is at a maximum? So when r is equal to 39.8942 blah blah blah. is equal to minus 6 pi times 39.8942, blah, 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 which is obviously going to be less than 0. Therefore, when R is equal to 39.8942, blah, 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 the maximum value occurs. Therefore, V is equal to 398,942, blah, 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 0.28, blah, 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 is max value of V. Okay, so we've done a few now, so you can see the steps to solving optimization problems. So what you should do is draw a diagram if it will help you. Set up the two equations, as there's always two equations, and sometimes because of the nature of the problem, because how they worded it, you might need to introduce some letters into these equations of your own. Eliminate always one variables, so you have something in terms of with respect. There's only two variables involved in your final equation. Differentiate and solve dy dx is equal to 0. Obviously, it doesn't necessarily have to be dy dx, but make it equation to 0 and solve it. Substitute this value into the original equation to find actual minimum maximum value, and use your second derivative to justify that this is a max minimum. Even if the question doesn't say, I just tend to do it just to make sure I've done it right. So check that I do. Okay, let's go to the next question. A large tank in the shape of a cuboid is to be made from 54 meters squared of sheet metal. Okay, so it's a cuboid we have here. So I'm just going to draw the cuboid out. The tank has a horizontal base and no top, so the top is missing. I'm just going to, no top, okay. So let's just highlight that. The height of the tank is x, so this is x. Two opposite vertical faces are squares. Two opposite vertical faces are squares. So it's this one and that one. So that means that must also be equal to x, because these are the vertical faces. Show that the volume V of the tank is given by this formula. Okay, so what we do know is the surface area is equal to 54. So surface area is equal to 54. But we also know that the surface area is equal to the sum of all the faces. So we know we need to introduce another unknown here. Let's call this y. Then the surface area would be from the two vertical faces, we get x squared plus x squared. And then the other faces, other three faces, remember the top is missing, so there's no top. From the other three faces, we get yx plus yx plus yx, which implies the surface area is equal to 2x squared plus 3xy, or yx. So we've got equation 1 and equation 2. So using 1 and 2, because they're both involve surface area, we end up getting 2x squared plus 3xy is equal to 54. And then we have to eliminate y. So that means, because I don't have a y in my v formula, which means I need to make y the subject of the formula. 3xy is equal to 54 minus 2x squared. So y is equal to 54 minus 2x squared divided by 3x. Now the volume formula is equal to x times y, which is equal to x squared y. But that means v is equal to x squared times, so if to call this 3, 54 minus 2x squared over 3x using 3. If I expand this out, v is equal to 54x squared over 3x minus 2x to the power of 4 over 3x. If I simplify this, I get 17. No, it's not 17. 54 divided by 3 is 18. 18x, because one of the x's disappears from the top and the bottom. 18x minus 2 over 3x cubed, which is what I wanted. Okay, next part B. Given that x can vary, use differentiation to find the maximum and minimum value of v. Maximum or minimum, okay, sorry. So first thing I need to do is differentiate v in terms of x. Differentiate v in terms of x. So I get 18 minus 2/3 times 3 gives me 2x squared. So at stationary point, dv dx is equal to 0, which implies 18 minus 2x squared is equal to 0, which means 18 is equal to 2x squared, which implies 18 divided by 2 is 9. 9 is equal to x squared, which implies x is equal to square root of 9, and we only take this positive square root of 9 because x is a length which is always going to be positive, so it's equal to 3. And this was measured in meters, so x is equal to 3 meters. Okay, so we need to find out whether first find out the maximum minimum. So that means v is equal to 18x minus 2/3 x cubed, which is equal to 18 times 3 minus 2/3 times 3 cubed. If you put that into a calculator, you get 36. So 36 meters cubed. So justify that v, the value of v I have found is a maximum. So if I want to justify, I do this, find the second derivative. So second derivative means I differentiate this. So when I differentiate that, I get minus 4x. And if I substitute x equals 3 into this, then I get minus 4 times 3, which is equal to minus 12, which is less than 0. Therefore, maximum occurs when x equals 3. Therefore, the volume v is equal to 36 meters cubed is max value of v. Okay, next example. A sector of a circle has area 100. So first thing I need to write down is area is equal to 100. Show that the perimeter of the sector is given by the formula, so on. So we also know the area formula is half r squared theta. So this is equation 1, this is equation 2. If I combine it, I get half r squared theta is equal to 100. Now we're trying to, if we look at it, we're trying to get everything in terms of r, which means I need to eliminate theta. So r squared theta is equal to 200, which means theta is equal to 200 over r squared. If I want to set up a formula for perimeter, then it's r, so it's going to be, this part is r, this part is also r, this is theta, so remember arc length is equal to r times theta. So perimeter is equal to r plus r, which is 2r plus r theta. So let's call this 3. So we can replace theta with obviously what we know from equation 3. So perimeter is equal to 2r plus r times 200 over r squared, which means perimeter is equal to 2r plus 200 over r, which is what we wanted to show. Now what we do know is also the area of circle is greater than the area of sector, because it's a sector of the circle, it's not the whole circle. So what we do know is pi r squared, which represents the area of the circle, must be greater than 100, because 100 is the area of the sector. We've been given that information, which means r squared must be greater than 100 over pi, which means r must be greater than square root of 100 over pi. Okay, so that's part A done. Part B, find the minimum value for the perimeter. Okay, so after first write perimeter in index form, so P is equal to 2r plus 200 r to the power minus 1. So dP, differentiating P with respect to r, gives me 2 from the first term, minus 200 r to the minus 2, which is the same thing as writing 2 minus 200 over r squared. So we know at minimum dP dr is equal to 0, which implies 2 minus 200 over r squared is equal to 0, which implies 200 over r squared is equal to 2, which means 200 over 2 is equal to r squared, which implies r squared is equal to 100, which means r is equal to square root of 100, which means r is equal to 10. And we have to take the positive value again, which is only taking the positive square root because radius has to be positive. So we know when r is equal to 10, we know that perimeter is equal to 2 times 10 plus 200 over 10. Let's call this 4. So using 4, which means P is equal to 20 plus 20 plus 20, which is equal to 40. The units were centimeters squared, so perimeter will be 40 centimeters. If I want to check, obviously, if this is a minimum value, I need to differentiate again to find the second derivative of this one. So I get, oh, and it's not that one, the one above it. So when I differentiate it, I get 400, positive 400, 400 r to the minus 3, and d squared p over dr squared at r is equal to 10 is going to be equal to 400 times 10 to the minus 3, which is going to be greater than 0. Therefore, minimum value occurs at r is equal to 10 centimeters. Therefore, minimum P value is P is equal to 40 centimeters. Okay, next example. A shape consists of rectangular base with semicircle top as shown. Given that the perimeter of the shape is 40 centimeters, so A is P is equal to 40. Show that its area A is given by this formula. Okay, so first thing is perimeter. Form the equation for perimeter. This is R, which means this part must be 2R. This has not been given a dimension, so let's call it X. And that is X. This part will be using a half, it's a half of the circumference of the circle. So it's 2 pi r divided by 2, which is equal to pi r. So perimeter will be equal to 2r plus 2x plus pi r. So if we combine these two, then we end up getting 2r plus 2x plus pi r is equal to 40. Now we're aiming for this, which has no x in it, so which means I need to rearrange to get rid of to make x the subject of the formula. So 2x will be equal to 40 minus 2r minus pi r. So x must be equal to 40 minus 2r minus pi r divided by 2. Okay, now the area of this, if I look at it, if I split it up here, that is equal to 2rx, and that part would be pi r squared divided by 2, so half pi r squared. So the area will be equal to half pi r squared plus 2rx, sorry, not 2 pi, 2rx. Okay, so if we call this equation 1, then I can replace x with a is equal to half pi r squared plus 2r times 40 minus 2r minus pi r over 2 using equation 1. So the 2 and the 2 here will cancel out. So I'm left with a is equal to half pi r squared plus 40r minus 2r squared minus pi r squared. Okay, if I rewrite it now, so I've got 40r from the second term minus 2r squared. Half pi r squared minus 1 lot of pi r squared gives you minus a half pi r squared, which is what we want. Hence, find the maximum value for the area of the shape. Then B, I need to differentiate A with respect to R. So I end up getting 40 minus 4r minus pi r. So at maximum, dA dr is equal to 0, which implies 40 minus 4r minus pi r is equal to 0, which means 4r plus pi r is equal to 40, which means if I factorize the left-hand side, 4 plus pi is equal to 40. So r is equal to 40 over 4 plus pi. So the area, if I go here, area will be equal to 40 times 40 over 4 plus pi minus 2 lots of 40 over 4 plus pi all squared minus a half times pi. Let's leave it in the form they gave it, which is equal to minus pi over 2 times 40 over 4 plus pi all cubed. I made a mistake. It's supposed to be pi. Oops. It's supposed to be a squared. Okay, so I know the last two terms can be factorized. So area will be equal to 40 times 40 over 4 plus pi. Because the 40 over 4 plus pi squared is a common factor, if I if I put 40 over 4 plus pi squared is a common factor, and I've got 2 plus pi over 2 here because I've got a negative in the front. So that's how I factorize these two. Now if I want to write this bracket in a common denominator, then I get A is equal to 40 times 40 over 4 plus pi. Okay, let's make it a bit bigger so it's easier to see. That's going to be 4 plus pi over 2 times 40 over 4 plus pi squared. So one lot of 4 plus pi will cancel out from the top and the bottom. So now that can be simplified to 40 times 40 over 4 plus pi. Because one lot of 4 plus pi on the top will cancel out with one lot from the bottom, then what I end up with is minus a half times 40 squared over 4 plus pi. Okay, so area will be equal to, if I multiply out the first term, I get 1600 over 4 plus pi. 40 squared is 1600, but if I times it by half, I get minus 800 over 4 plus pi. Denominator is the same, so all I end up with is 800 over 4 plus pi. It's therefore maximum A is equal to 800 over 4 plus pi, and it was measured using centimeters, so centimeters cubed. Okay, if I need to verify this, then I need to differentiate twice. So d squared A over dr squared, and I'm differentiating this. Then when I differentiate this, I get minus 4 minus pi, which is always less than 0. Therefore, maximum occurs at R is equal to 40 over 4 plus pi. Okay, one last example. The shape in a wireframe in the form of a large rectangle is split by parallel lengths of wire into 12 smaller equal size rectangles. Given that the total length of the wire used to complete the whole frame is 1512 millimeters, show that the area of the whole shape A is given by the formula, so on. Okay, so A, we know the total area, should we call it total area, is equal to 1512. If we were to form an equation for the total area, we get 1, 2, 3, 4, 5, 6, 6 again here, and 6 over there. So that gives me 18 lots of X. We've got 2, 4, 6, 8, 10, 12, 14 lots of Y. If we put these equations together, then we get 18x plus 14y is equal to 1512. We don't have y in our formula for area, which means, and to make y the subject of the formula, so 14y is equal to 1512, take away 18x. So y is equal to 1512, take away 18x over 14. Okay, the area is equal to length times width, which is equal to 2x times, not 2x, sorry, 2y, which is 2y times 6x, which is equal to 12xy. But the y can be replaced with 12x times 1512, take away 18x over 14, using 1. If I use a calculator to expand and simplify it, then I get, for the first term, I get 1296x. And when I do 12x times minus 18x divided by 14, I get minus 108 over 7 x squared. Okay, B. Hence, find the maximum area which can be enclosed in this way. So I need to differentiate A in terms of x with respect to x. So I get 1296 minus 108 times 2 is 216 over 7 x. At max, we have dA dx is equal to 0, which implies 1296 minus 216 over 7x is equal to 0, which means I have 216 over 7x is equal to 1296. So x is equal to 1296 times 7 divided by 216, which is equal to 42 millimeters. Okay, so when x equals 42, A is equal to, using this one, A is equal to 1296 times 42, take away 188 over 7 times 42 squared, which is equal to 27216 from my calculator, and it's equal to millimeters squared. If I want to check that this is when the maximum occurs, I need to differentiate A again. So to find a second derivative, so d squared A over dx squared, which is equal to minus 216 over 7, which is always less than 0. Therefore, max occurs when x equals 42. Therefore, maximum area is equal to 27216 millimeters squared. And as a last bit, just to keep in hand, they won't give you this formula in an exam. These are some formula that might come useful when you're looking at surface area and volume of 3D shapes.